Hi everyone, thanks for joining me today to celebrate video number 1000 on my channel. So, who would have thought when I started this channel that it would one day feature so many videos? Certainly not me, at least at the beginning. So once again I would like to thank all of you for viewing videos and subscribing and commenting and giving nice ideas for the contents. Without your suggestions I would probably have stopped making these videos long ago. Now, what do you do for such a milestone? Well, on previous occasions, meaning every multiple of 100 videos, I did something special, like maybe the first video with a new program, simulating a new type of system or equation, or maybe a video that was harder to make than the typical videos, or some kind of crossover between different types of simulations I made. Now, I spent some time thinking about what to do in this case, and I finally came up with this idea that it would be interesting to review all the 9 previous milestones, but adding comments on my parts with the information on how this video was made or how this particular simulation came to be. So this is what we're going to do. But first let me just give you some background on how my channel was created in the first place. So in a way the culprit is UNESCO, when they declared that 2013 would be the year of mathematics of planet Earth. This prompted a number of initiatives, one of them being to make a kind of blog with daily short articles illustrating how mathematics is used to model different aspects of the Earth. The idea originated in Canada, but was then taken over by colleagues in France, and I learned about it at a meeting, I think it was in November 2012, from a colleague who was looking for people willing to write articles for this initiative. And I immediately thought of stochastic resonance, which is a phenomenon that actually appeared originally in a climate model, and I'm talking about that in one of my videos on climate models. And I proposed that to my colleague, who said yes, that's a good idea, so go ahead or write an article, short article on that. Now, one constraint in this blog was that it should not contain any equations, so it should describe the phenomenon and the mathematical results only in words and pictures. So I wrote a small description and then thought that it would be so much nicer, instead of just having a picture, to have an animation of that. And I didn't know at the time how to make animations, though I knew how to make these simulations on my computer, but I asked around and it turned out to be quite easy to make videos from sequences of images from such a computer animation. And I asked my colleague whether it would be possible to include a simulation, and he said yes, but the website does not have a video support as such, so it would be better to put the video on a site such as YouTube and embed a link to that site. So that's what I did, and this initiative of mathematics for planet Earth, so the French part, gave rise to this little book where a number of these short stories about mathematics applied to geology and similar things are described, including my contribution. Now, once I had created this YouTube channel, I produced a number of videos in the weeks and months after that, many of which I used actually to illustrate articles I occasionally write for a French website called Images des Mathématiques, Images of Mathematics. Again, because some of these things I was writing about are best illustrated by small simulations. And in the next 7-8 years, I made not a large number, maybe 40 simulations on the channel, either for this website or sometimes when I made a few simulations related to my research. And then in early April 2021, something surprising happened. So it wasn't on April Fool's Day, it was 1 or 2 days later. I have this bad habit of, when I take my breakfast in the morning, reading my email and watching a few news websites, and then I was just about to close my browser and cycle to work when I suddenly realized that in at one place in the browser there was a little 88 shown. So of course 88 made me think of Quentin Tarantino, but then it turned out that this 88 was the number of comments that had appeared in the last couple of days on my YouTube channel. And what I understood from the comments was that actually the algorithm had kind of discovered a couple of my old videos on billiards and the Ehrenfest model. And these two videos had gotten a large number of views, and 88 was the number of comments. And most of these comments were very positive, so people saying that, okay, it was a fascinating simulation, but there were also criticisms, mainly saying that the simulation was too short and maybe also too low resolution. So, well, if I can do something to make people happy, of course I like doing it, and so I was a bit reluctant at first. I wasn't even sure, I hadn't used this code in quite a while, whether it would compute all right, but I tried and it did, and so I started making some new versions, longer versions, higher resolution versions. And then I mentioned this to some colleagues, and they gave me some ideas of new things to simulate. And so it went on from there. So ever since, I've been making improvements, first in resolution, then adding new color gradients, also adding music. I started this early on. Then I moved also to three-dimensional visualizations. I added more and more different systems. I made shorts and I made tutorials and so on. So let's now move to the first milestone. So I started making these regular videos in April 2021, and since I had already 40 videos, I reached 100 videos at the end of May in 2021. So there up to then I had mainly made videos of billiards and a few other things like the wave equation. And so the idea I came up with to celebrate this first milestone was to make a more complicated billiard. And so I decided to make a video where 100,000 particles are moving in a billiard with 100 sides, and these sides are actually circular arcs that curve inward and meet at right angles. And the reason for that is that if the angles of the billiard are divisors of 180 degrees, then if you have a front of particles hitting the angle, the front is not cut into small pieces, so it gives you a more orderly simulation, at least at the beginning. So this was at the time probably the most computationally intensive simulation I made because of the large number of particles, and for each particle you have to test intersections with 100 different arcs of circle. Now, of course, in the meantime, I've made simulations that take much more computations to do. But okay, so that was the simulation, and as a soundtrack I chose a piece called Loud in the Cloud by Nana Kwabena, mainly because it is kind of a festive music, so I found that the style of this music fit the celebratory nature of this first milestone. So let's have a look at this video. The second milestone, video 200, I published in early September 2021, and that has actually an interesting story behind it. So, after making my first videos of billiards, I got requests of doing the same for the wave equation, which I did. And then at some point in a comment, someone suggested I also simulate the heat equation. Now, I knew that the heat equation tends to be quite boring because the heat just tends to spread uniformly everywhere unless you use interesting boundary conditions. And one way of doing that is to use a fractal boundary. And I did a few simulations of the heat equation with fractal boundaries, and once I had coded those, it was natural to do the same with the wave equation. So at some point I made a video with waves hitting various approximations of a Sierpinski carpet, and then I got this comment here, which is probably the comment with the most likes on my channel. You see there are over 6,000 likes, and the comment was saying, and now you understand why mangroves are important for coastlines. And this, of course, is a good remark, and the fact that so many people liked it I found quite comforting, meaning that many people are concerned and do care about our coastlines and maintaining a natural vegetation. And this led to a whole series of mangrove versus tsunami videos where I compared the efficiency of different wave protections, so different geometries of putting obstacles to break the waves. And then I started getting comments on, well, it would be nice to have something that looks more like a living mangrove, so it could be so obstacles that erode over time, so that I did, so like the mangroves get damaged by a storm and shrink, or even moving mangroves. So that seemed a bit more difficult to do at the beginning, but finally it turned out that it was doable. It takes a bit longer to simulate because whenever you move a mangrove, you have to re-initialize the table telling you which points are in the domain of the wave, or where you have a certain speed of propagation, and which points are in the mangroves where you have a different speed of propagation. But I managed to code this, and what we are going to watch is the first simulation where the mangroves move. So I did better simulations later on. In this first simulation, the mangroves actually can overlap, so there's no repulsion between them. But at least it showed that this kind of simulation was possible, and actually it also laid the groundwork for later simulations on interacting particle systems, because what I coded for these mangroves, the way I represented them is quite similar to these particles interacting with Lennard-Jones potentials. So this one took 67 minutes to render, and the soundtrack is called September Pass, and it's by an artist named Asher Falego. Not sure I'm saying the name right. And it's an artist I really like using the music, so because he has very atmospheric pieces. So let's have a look at this video. The third milestone, video 300, I published in early December 2021, and it features waves in a polygon with 128 sides. Now, the new thing about this video is that it's the first video I published in a higher resolution of 1080 points, which may seem as a small improvement, but actually all previous videos had been in lower resolution, and simulating the wave equation in this higher resolution was only possible because of some improvements in the simulation algorithms. And the another thing that I started doing slightly before this video was to use better color gradients. In fact, in most of my first simulations, I used a color scheme called HSL, for hue, saturation, luminosity, which is something I've found online at some point that translates, so the hue is the type of color, blue, green, red, and so on. Saturation is how bright the colors are, and luminosity is just whether it is closer to whether it is dark or light. And there's a conversion of that in RGB, red, green, blue code, which I found and that you can use. But people criticized this, especially for the wave equation, because this color scheme is not perceptually uniform, meaning that if you have large patches of maybe red inside blue, the areas appear larger or smaller. So perceptually uniform color gradients avoid this problem, and there are a number of these gradients available, and the one I use here is called Inferno. And another advantage of these color gradients is that they are usually better for colorblind people. So in the other HSL gradient, some colors may just not be distinguishable by colorblind people. So in this video I use, as quite often, two parts representing first the wave height and second the wave energy. The render time was 25 minutes and 15 seconds, and the soundtrack, because that was in the holiday period, I used a piece called Canon and Variation by Twin Musicom, which I suspect is strongly inspired by Pachelbel's Canon in D, which is a piece I know very well because I discovered it as a kid. A friend of mine had a version of that on his computer, and I was so fascinated by this piece that I wanted to learn to play it on the piano, but it's actually written for strings. So what I did is that I took there was a score together with this version that my friend had on his computer, so I printed that and used that to play it on the piano. So let's have a look at that video. Video number 400 I published in March 2022, and it's the first video I made in 3 dimensions. So in the first year I quite often got comments from people asking me to do 3-dimensional versions of my videos. And first I was a bit reluctant because I was concerned about the computing time for that. Now it turns out that if you really want to simulate something like the wave equation in 3 dimensions, that takes a lot of computation time unless you use a very low resolution, because you have to use many more points where you simulate the equation. So this you can actually only do with a reasonable resolution if you use a GPU. But what is a bit easier to do is to simulate a 2-dimensional wave equation, but to plot things using the 3rd dimension to show, for instance, the wave height. Now, I had 2 options for doing that. One of them, since I'm using libraries from OpenGL for the graphics, was to use built-in functions in OpenGL to make a 3D rendering of graphics. But I was a bit concerned about, again, the time it would take to render these if you use very complicated lighting models, for instance. Then I chose the other option, which was to code this myself. I had done it before, and it's not so difficult. Actually, the first thing I did was to use just what is called axonometry, where you just use a linear map from 3D to 2D. So you take your 3 basis vectors and you project them on 2D. And that is what you are going to see in this first video. But later on I moved to something which is really where you project the 3D object on a 2D surface, and that gives you, for instance, perspective with a horizon, and so more realistic way of representing 3D. In this particular video, so my very first one in 3D, we have waves in an ellipse starting from a focus, so which I had simulated before in 2D, and the render time is 44 minutes, and there are two parts. The first one showing the amplitude in a color scheme called Twilight, and the second one in Viridis actually also shows the amplitude, but I chose a color depending on the angle between the normal vector to the surface and a fixed direction. So it was the first try in using a lighting model in 3D. And it was my first simulation in 3D, so there are some issues. So the resolution is not so great. I later improved it by using some interpolation, and also I later improved the color gradient. But okay, let's have a look. And the soundtrack is called Dreamer, and that's by an artist with the name DivKid, who does rather electronic sounding pieces. And this one I kind of liked because of the feel that the music gives. So let's have a look. On the 1st of July 2022, I reached another milestone, which was video number 500. So I had to do something a little bit more special, I thought. And one thing I had wanted to do for quite a while, I'm mostly using music from the YouTube audio library, and most of the tracks there have durations between maybe 2 and 4 or 5 minutes, but there are a few very long tracks. And one of them is the final movement of Beethoven's Ninth Symphony, which is a piece I like quite a lot. Some of you may associate it more with Bruce Willis killing bad guys in Nakatomi Tower, but yeah, it's actually a nice classical piece, and it is quite long, over 23 minutes. So for a long time I wondered how to use this track, because it takes a lot of time to render a video of the wave equation, and also when you store all the images it takes a lot of memory space. So I wasn't even sure would be able to store all these images. So for each minute you need 1,500 images, and until you make the movie they are in uncompressed form. But then I had this idea that I could actually split the video in several parts and put them together at the end, which is not so hard to do using FFmpeg. And so what I did is that I looked closely at how this final movement of the Ninth Symphony is made, and it's actually made of a large number of small pieces, which I grouped into eight fragments. So it starts with an introduction, then you have the exposition of the joy theme and the 3 first variations. Then you have a part with a choir and 3 more variations, and then it goes on with more variations, a kind of central piece, and the ending parts. And to each of them I associated a video, and I chose as a common theme videos featuring the billiard in an ellipse, so classical particles for the first 2 parts, and then several parts with the wave equation, and so first in 2D and then in 3D, and finally 2 parts with the Schrödinger equation. And in the final case it's the Schrödinger equation with a Coulomb potential inside the ellipse. So this is a rather long part, so let's have a look.
nicht diese Töne, sondern lasst uns angenehmere anstimmen und
Video number 600 I published in October 2022, and it was my first video on a system in fluid dynamics called the incompressible Euler equations. So equations in fluid dynamics are nonlinear, and that makes them more unstable and therefore harder to simulate. The wave equation is a linear equation, and in addition it conserves the energy, so that makes it quite stable in simulations. While in nonlinear equations you can have a phenomenon called blow-up. Now, I already had made quite a number of simulations of reaction diffusion equations, such as the Allen-Kahn equation, but these are, they have a strong dissipation, and that tends to prevent blow-up. But in fluid equations, you typically have what is called the advective term, which is a v times gradient v term, and that one can be the source of blow-up. So actually there are cases like the Navier-Stokes equation in 3 dimensions where it's not even known whether you can have blow-up in large time. So blow-up does not mean so much that the amplitude of the velocity field becomes large and diverges. It's more like you get oscillations. So what can appear is that the solutions oscillate more and more, and then you can have the appearance of shocks. And this makes it harder to simulate the equation, so you either have to use smaller time steps or some other trick to detect an impeding blow-up and prevent it. So what I actually did in these equations is that usually I added some dissipation. So the Euler equation becomes more like a Navier-Stokes equation. So the particular video we are going to show here is showing 2 interacting vortices. So you use a particular initial state that has a certain vorticity. Actually, 2 parts of the fluid rotate in different directions, and that will create these nice vortices. So the render time here was quite long, almost 3 hours. And that is because I was probably a bit overcautious in taking the time step. Later on I figured out how large I could take the time step and still have a simulation that does not blow up if you don't let the simulation run for too long. So there are 2 parts with 2 color gradients, viridis and plasma, but showing the same information, and the soundtrack is called Clouds by Humor. Video number 700 I published in January 2023, and it is a tribute to Sir John Lennard-Jones, who is the inventor of this potential, so in interacting particle systems, that I use a lot in simulations because it's quite stable to simulate. And it features the simulation of a breaking dam. And I had made simulations of breaking dams before. What is new here is that I actually wanted the particles to form an image of John Lennard-Jones at the end of the simulation. So I had already made a couple of simulations for Christmas and New Year where I used this reverse engineering of the simulation to create a certain image in the end. And the way I did that is that I actually ran the simulation twice. So first I just simulated the motion of the particles and stored all the information in a big file. And then I rendered the simulation, but I chose the color of the different particles depending on what I wanted to see at the end of the simulation. Now, the first two simulations I made with very simple geometric shapes, like a Christmas tree and text saying Happy New Year. But in this one, I needed to use a photograph of John Lennard-Jones, and I had to learn how to do that. So first I looked into some libraries in C that enable you to handle images. But then I found quite a simple solution, which is to load the image you want to use in a graphics program. So I used GIMP, but you could use many other programs, and then to export it after adjusting the resolution. Export it in a bitmap format, so in a PPM format, with the option that it is saved in ASCII. And that means that it will produce a rather large file, but this file is easily readable by C code. Actually, it has lots and lots of numbers containing just values of RGB codes. So this I knew how to read with a program, and then process it to do what I wanted to do. So this one took me a bit over an hour to make the computation of the particles, and then a bit over 8 minutes to render the movie using the information in this big file with all the particle positions. So the color gradient is turbo, and the soundtrack is Orange Sunset by Quincas Moreira. So let's have a look. The milestone number 8, video 800, I published in April 2023, and it is actually a crossover between two types of simulations I have been doing for a while. So one of them is simulations of rockets. So I had started with a very simple simulation where my rocket is just an elliptical enclosure containing Lennard-Jones particles that you heat up by coupling them with a thermostat and increasing the temperature. And then at some point you open a little hole in the enclosure and the gas will leave the enclosure, and because of the action-reaction principle or conservation of momentum, your rocket will start accelerating in the opposite direction of the opening in the enclosure. Now, I had made quite a few simulations where I improved the shape of the rocket, and in particular adding nozzles of different shapes. And in parallel, a bit later, in early 2023, I started simulating chemical reactions. So this means that I take particles of two or more different types, and these particles have a certain probability to react to produce new particles or molecules when they are close to each other. So that's of course a simplification of what happens in real life, but so if, for instance, you want to simulate the reaction A plus B gives C, so you start with a certain number of A molecules and B molecules, and then at regular time intervals, you check for each molecule. For instance, if it's type A, you look if there's a B molecule around in a certain radius, and if that is the case, with a certain probability, you replace these two molecules by a new C molecule. And you can do that, of course, with more different types of molecules. So in this video, I have taken a rocket containing two types of molecules, and they react, and the reaction is exothermic, which is modeled by increasing the temperature of the thermostat, but really depending on the number of reaction you have. So we are going to see the first simulation of that type I did, and it has 4 parts. So the first 2 parts show a low reaction rate, and it's first a time lapse and then a normal speed version, and it took a bit over 10 minutes to render. And in the second part there's a higher reaction rate, and which will imply that the rocket is able to go higher because more energy is created, and the render time was 8 minutes 38 seconds. And so the color gradient is turbo, and for the soundtrack I appealed again to my friend Ludwig van, and I used a piece called the Egmont Overture, which I found matched the simulation quite well, especially the very last part when the rocket finally managed to reach a certain height, had a certain uplifting spirit that I found worked well with the video. So let's have a look. The last milestone video we are going to see today, I published in early August 2023, and it's my first simulation of the wave equation on a sphere. So I had made lots of simulations of the wave equation in planar domains rendered in 2D or 3D. So transposing this to the sphere is actually not so difficult. What you have to do is you change the definition of the Laplacian in the wave equation, meaning that if you use longitude and latitude so to describe your sphere, you have to use the expression of the Laplacian in spherical coordinates for constant radius, and it means that you have some latitude-dependent coefficients in the equation, and also you have a first-order derivative appearing. Now there are some difficulties near the poles because these corrective terms increase the wave speed and it diverges at the poles, so that is something which in this first simulations we are going to see I solved in a way which is not optimal and creates some reflections on the poles. I managed to improve it later on, though there's still some room for improving the simulation. Actually, I know how to do it. I just haven't had the time to really improve this to some optimum simulation. But anyway, we are going to see a first instance of simulation on the sphere, which is just the impact or some wave that could be a meteor impact on a planet entirely covered by water. But this led later to many recent simulations of asteroid impacts or also volcanic eruptions and earthquakes on the Earth and on other planets. So the simulation we are going to see took a bit over 31 minutes to render, and there's a first part showing the wave height with a Viridis color gradient, and a second part showing the wave energy with a plasma color gradient. And the soundtrack I used, it's a track called Xenon by Fast Music, who contacted me in a comment proposing that I use some of his music. And that artist is composing so-called microtonal music that uses smaller intervals than the tones and halftones we typically use in Western music. And I chose that piece because I found that these small intervals gave some kind of eerie quality that matched quite well this scenario of some meteor or asteroid impact on a distant planet somewhere in the universe. So let's have a look. Alright, so that was this retrospective of 9 highlights on my channel in the last couple of years. I hope you enjoyed it. Now, here is just an advertisement for some upcoming highlights in the next few days. So there's going to be a video of an asteroid impact on a partially flooded moon. There's going to be a new collaboration with Huygens Optics on something called numerical aperture. And there's also going to be a video on ionization of a gas in order to form a plasma. So thanks again for watching and for giving ideas for new videos. So please keep giving these ideas to help me make new videos. So I'm not planning on stopping in the near future, so I think we can expect some more interesting simulations in the time to come. So thanks again a lot for watching. I hope you liked this, and I hope to see you again very soon. Take care. Bye.